In order to properly tell you this story, I need us to rewind back over a year ago to October of 2022. I released a video where I tried to show how difficult it can be to fabricate simple shapes and the obstacles fabricators need to be aware of. At the end of that video, I suggested a fixture table to help solve all these problems.
Look at the accuracy that you have with a table like this. This is incredible.
And some people had a few things to say about all that. Things like, Jason, you are an idiot. I can do all those things without that table. That table is pointless. If you have enough skill, you don't need a fixture table. With that exact line, I decided to test that theory. So I created a little experiment, and that brings us to video number 2. So 5 months later, in March 2023, I paid 3 professional fabricators to build me the exact same frame that I had made in the first video, and made sure none of them had a fixture table, because if they have enough skill, then surely they wouldn't need a fixture table, right?
Oh yeah, I got a steel table.
As I tested them, I was surprised to find that they all failed, and concluded that none of them were able to match the drawings that I gave them. This experiment has got me curious. I don't know why all 6 of these frames are failing. Something very strange is going on here, and I think we need to discover why. This mystery has me thinking we need a new approach. After all, you guys on the Fireball forum had some suggestions as to why these frames turned out the way they did. So let's concoct a new experiment. Some of you said we need to communicate better with more detailed plans. Others said the job wasn't taken seriously because the part was too simple, so the next part needs to be a bit more complex. And finally, it was stated that our testing method was biased, so I'll make sure to test these new frames with something extreme. So for this new challenge, I'm gonna cook up something spicier. 3 new fabricators will have to make this plan twice. We're gonna start with our original square frame that we had last time, and then add 4 stub legs that gets welded perpendicular to the original box frame, kind of creating a table, but not really. A little bit later, I'm gonna explain why this test is difficult and what makes this the perfect challenge. Hopefully the welders can identify the problems with this test and solve them. Let's take a look at the drawing. I made sure that we have weld callouts, weld sizes, materials, lengths, heights, and even a cut list for the fabricators to follow. If they can't make it from this design sheet, then there's some serious issues we're gonna have to address later. If you'd like to get a closer look at the drawings and follow along with the build, I've made the plans available to download at the Fireball Tool forum. This brings us to August 2023. So, only one more thing left to do, get the plans in the hands of the fabricators. I'd like to go to 3 different fab shops than I did last time. This is gonna increase our sample size. Like the previous video, I'm gonna keep the fab shops and welders' identities hidden, because I don't wanna make anybody uncomfortable. We're gonna drop these drawings off in person. This is gonna give us the opportunity to ask the fabricators a few questions, like, what strategy would they use to build this? And did the drawings look okay to you?
Yeah, it shouldn't be that big of a deal. Flat table, put it together and put your legs on, square them up, and you're done.
Sounds easy enough to me.
That's easy. And they actually gave us a cut list. Oh, it's really surprising. They never give us good stuff like this. I like whoever made this print.
Challenge accepted.
I want to remind everybody at this point that all the fab shops and fabricators are using a plate steel workbench table. So that got me thinking, how would I build this simple test? I think there's 3 different methods, so let's talk about the first one. I think I would start by building the square frame first, and then when that's all welded, I would start standing all 4 legs up and get those welded to the frame. So let's talk about method number 2, which is a completely different approach. This method starts with the legs and gets it welded to the sides first. At this point, you've constructed 4 T-joints, and now you combine all 4 T-joints to make the box frame. Method number 3 puts the emphasis on making 2 identical parts, and you can do this by making 2 box frames, welding all 4 legs together, creating one big large weldment, and then coming back and cutting it apart in the center. Whatever method they choose, they have to make 2 identical parts. So here's what makes this test also difficult. So it's not uncommon for a welder to build one part and then try to make a copy from it. This weldment is difficult to do that because of its geometry. You cannot stack the parts on top of each other and recreate one from another. And then, whatever method they choose, they're going to be fighting weld distortion. On this test, you're probably noticing that the leg is not in the corner. Well, that's on purpose, because what I want to see is how the welder's going to handle weld distortion. So we've placed the leg right in the center of the tube, and this is going to add a whole nother element of trouble. So as we wait for the fab shops to build the frames, I think we should do a little experiment right here on the table and see how much distortion these guys are actually dealing with. Now I've set up a little sample right here of this exact length tube, 20 inches, and we're gonna weld this little stub piece all the way around as a control to see how much distortion we're actually gonna get. I'm gonna put weld seam opposite of our little stub shaft so everything's consistent here. We don't want the seam to add any extra weird stresses into our test. For this first one, I'm gonna tack it all the way around, weld the sides, and then do the fillets last. If you're already a welder, this is just something we deal with every day, and we can predict how much it's gonna warp. But I think this is a good demonstration for those of you guys who haven't seen this before. These aren't overly sized welds. The plans call out for 1/8 of an inch minimum. I could definitely TIG this, but if you wanna make money, you're probably gonna be wire feeding it. So we're gonna let this cool for a second, and then we're gonna test to see how much distortion there really is as we wait for the weld to cool. There's a lot of heat concentrated in this area, and as it slowly cools, it just slowly pulls, shrinking on each side. And as that does, it pulls this up. This isn't my first rodeo, boys. I know she's gonna get rowdy over here. She's gonna do buck and bronco. Wee-haw! Okay, I think she's cooled down enough to go test on the surface plate to see where we ended up. Now I'm just gonna teeter it. It's bowed up quite a bit. You can see some light through there. So how much distortion are we talking here? I have my fireball shims. Let's see if a 1/16 will slip underneath the edges of that. Almost a 1/16 of an inch. 32nd maybe. So not quite a 1/16, but definitely more than a 32nd. So if the fab shops don't do anything to their material, they're most likely gonna get at least a 32nd to 1/16 of an inch of distortion. Now let's see some other ways they can fix this. Let's clamp this next one down and test it. Weld goes down, part goes on top, and we clamp it to this 2.5 inch thick plate steel table. That's gonna fix it, isn't it? Not going anywhere. Now let's weld it. Same thing as last time. Tack it first, then weld it. It's cooled off now, so let's take it over to the surface plate and see what we got. Let's put her down here and see how she does. I'm just gonna teeter it. Here's a 32nd of an inch, goes underneath. Here's our 1/16. Here's the control. Here's our first weld, second weld. I think they're almost identical. Maybe this is a little bit better, the one we clamped down, but in all reality, they're the same. Same piece of material, not welded. As you can see, it's perfectly flat. As flat as a piece of tubing gets. That's what makes this test so valuable, is I know that this is gonna happen. Every welder's nightmare is just dealing with distortion, and it's very predictable.
I am inevitable.
So you're probably saying, Jason, you didn't leave it clamped in long enough. A minute is too short. You should have left it in until it completely cooled. We can do that test too if we want to, but in all reality, if you have to wait more than a minute to do one weld at a time, it's gonna take you forever. So we know clamping doesn't work. We know just welding it in the open air doesn't work. The next option is to anticipate the distortion. The only way I've known to really fix this is to pre-bend it. Now I'm gonna use the fireball shims here. I got all assortments. We just showed that it at least has a 1/32nd of distortion. We know it's probably a little bit more than that, but I think this is gonna be pretty close. So what I wanna do is pre-bend this tube that same amount. So I'm gonna put these two shims together, and they're basically gonna be positioned right underneath the fillet welds. And when I put this tube steel down, you can see that it teeters about just as much as it distorted last time. See the gap over there? I'm gonna bend this tube the other way. You gotta have big, heavy, substantial table. Now we got a good bend in it. Let's weld this guy down right over the top of those shims, and then let's see what happens. Okay, we'll let that cool for the next minute or so. Let's pull them out. Shimmed, pre-bent piece of tube steel. I can barely see it moving. It has a little wiggle in it. that would definitely be in spec. I don't know, you probably can't even see it come up on camera. It is barely wiggling, but that is a big improvement. So we know the pre-bend works really well before welding. But what happens if they did bow it and warp it? Do they have to start over, or can we fix it? So in order to fix this, we're gonna need something flat. I would use this big piece of plate steel to straighten this piece up, but it's really not perfect. As you can see here, my plate steel table has an 1/8 of an inch dish in it. So unfortunately, it doesn't make a good surface for inspecting my fabrication. Throughout this experiment, I've been using the granite surface plate to check flatness, but I'm unable to fabricate with it. So instead, I'm going to use something that I can do both with, the fixture table. So let's go over to the fixture table, and I'll show you how we can do it there. So now I have a good reference surface. I know this is flat, I know this is straight. So I'm gonna do the same thing I did before, but I'm not gonna be able to use these 1/32 shims, that I'm gonna have to beef it up. I'm gonna need to really stretch it. So I'm gonna use these 1/8 inch shims. I'm gonna go underneath here where I had that before. Remember, this is our control. This is the one that's bowed and has all that distortion in it. And we're gonna try to straighten it out. Clamp it all down. I know this tube is pretty stiff, so I'm gonna get it clamped, and then I'm gonna add just a little heat back into it, and we'll straighten it up. I'm just gonna warm up the fillets a little bit because I know that's where all the stress is at. This is the long way. Don't make this mistake. Okay. Let that cool down. Okay, so we've taken all the tension and stresses out of the welds. Even though this is still a little warm, we've relieved it so it should stay. And it did. It stayed pretty flat. So those are some things we'll look for when we get ours back, as if they had to fix it. Because you can see a little heat distortion around it. There's also a few more reasons why I chose this table shape for this experiment. And the first is that all 4 legs are completely unsupported at the ends. What this means is that it's going to be difficult to keep everything straight, plumb, true, and perpendicular to the base. Worst case scenario, you have welded the legs crooked, and now you want to adjust them. Unfortunately, if you try to straighten the legs, it's going to cause some problems. For example, leg condition 1, legs are splayed out evenly. Well, you could put a clamp on them and pull them straight. Same goes if the legs are splayed in. You can get a clamp, reverse it, and push the legs back out. What you're probably really doing is twisting, pulling, or bending the base. Unfortunately, that's going to make the base even less flat than it probably is to start with. Here's condition number 2. One leg tilted in, one leg tilted out. Unfortunately, the clamping method to fix this is not going to work, because as you clamp, yes, one leg is straightening, but the other one is getting worse. Here's another compounding issue. Yes, you've straightened the legs up, but you twisted the base. But did you think about the leg length changing at the same time? That's gonna make things teeter-totter. So we're stacking up compounding issues here. I'm sure you're thinking, Jason, you're making a bigger deal out of this than it really is. Well, I guess it's time to find out. Let's pick up the parts and see how these fabricators did. When I arrived at the first shop, I was immediately asked,
Really for?
So I explained to him that he was a control for a big experiment, and that he was representing welders with plate steel tables. And I was going to be looking at how accurate this frame was welded and put together. I also told him I was going to be asking questions that you guys left me on the Fireball forum from the last video. So the first question I asked was how difficult he thought it was to weld together.
Why would it be difficult?
So I explained to him the concept we explored earlier, weld distortion.
I mean, tacking it up, it isn't a problem, but yeah, when you weld it out, then things move on you.
Yep. Now that we were on the same page about the existence of weld distortion, I asked him how he made sure the part was right and correct to the drawing.
Well, tape measure, square. So if you got a little weld sticking out, but if you check your squareness,
Okay.
and if it was upside down, so this one pulled out a little bit, supposed to be 20 1/4.
Wait a second. Did he just tell me this is wrong? Even though he said,
Yeah, it shouldn't be that big of a deal. And this is right at 20.
okay,
So the bottoms and the top,
right.
same.
Theoretically should be right. And then I asked him this. Do you have a way to check flatness?
Well, when I put you kind of level those four pieces
Okay.
when you tack them together.
Okay.
And if they're level
Yeah.
when you tack them together,
Theoretically, they should stay, huh?
I mean, you don't see any gaps there, right?
I wanted to know if he felt he had the right tools to check if the work he's creating actually is flat. Is that table good enough to test for flatness? I'll take that as a no. I told him the twist and flatness is important to me, because what happens if I wanted to put a piece of glass on top of this frame?
Well, if you were going to put a piece of glass on there, you would have four cushions of some sort rubbing, so glass isn't rubbed on metal with it.
Absolutely. But wouldn't the cushions be the same height? So no matter what, if one's lower, you'd have one that would teeter-totter on? This conversation went on for a little bit, and it was great picking his brain. And I don't want to waste any more of his time because I'm sure he's busy, so on to the next fab shop. When I got to fab shop number 2, I also took the opportunity to ask a lot of questions. What was his technique to get the frames as close to tolerance as possible?
I go off the table. For something this small, I center it up in the table. My table's kind of like that a little bit.
Okay.
So something like that, if I put it right in the middle, it's good. Bigger projects, I'll put angle finders on it. It's a digital reader within like a half a degree. So like if I got two pieces in, I'll zero this one out and then match this one to that. But for something this small, I just put it right in the center of the table.
Basically what he's saying is that because his table's so crowned, that it's really difficult to use it as a reference surface, or use a square. So he's decided to use the level method and use that as the reference. I have a hard time believing that this is the fastest way to build this, because in fab shops, time is money, and this is where you make your profit. With my parts in hand, made with a level, it was time to go to shop number 3. So how were they? Were they hard to build?
No.
Easy peasy.
Easy peasy.
Perfect. How flat is your table, do you know?
At this point,
Not
so.
Not so.
I mean, it's one of those things that typically I throw a level on anything if I'm like, okay, this is something that actually has to be precise.
Right.
We've talked about it, but it's just one of those things of getting an actual fixture table.
So how are you holding stuff in the middle of the table? Are you welding it down?
If we have to, we put it in the middle, or we just do everything off of an edge as best we can.
Yeah.
We get creative with clamping, and
All right.
we got to do what we got to do to make it happen.
Can I ask you how long it took you to make them?
About 2 hours.
2 hours so an hour a piece?
Basically, yeah.
So here's how the cost breaks down. Generally, materials are about $130. Labor is about 2 hours, and you can vary between $100 to $170 an hour depending on the shop. So the total is around $470, unless this happens.
If they come in and they say it's wrong, we fix it. It's what it is, If they gave us a spec.
So then, if it's fixed on their time, they're out the labor costs, and maybe even more material costs too. But we won't know if that's going to be the case until they're tested. But before we do that, let's take a quick look at them. After all, I find it strange how each fabricator said this was going to be an easy job to do. And what's inside? Man, there's all these stuff inside of these tubes. What are they packing in there? I'm just gonna clamp this to the table of this tube. I'm just gonna look at the roll. But these are just visual inspection stuff that you can do before the customer gets it. You can see that this tube is extremely twisted. It might actually still be in spec. It's just strange to me. In order to know whether or not these actually follow the drawings, we have to test them. The last time I tested frames, I used my fixture table and set up some positive stops, used a dial caliper, and used the surface plate to do some measuring. But as was suggested on the forum, I'm taking it a step further. So this time we're going the extra mile. I'm going to be using a CMM, or Coordinate Measuring Machine. Let me show you how it works. A CMM is a giant camera that looks towards an object, and then a probe is used to touch various points on the object. This machine can measure down to the thousandth of an inch. The camera sees where the probe is touching and creates coordinates. These coordinates are fed into a computer to create a perfect 3D recreation of the object. And this is what's going to tell us if the frames pass or fail the drawings. So who's going to be running this machine? Well, I'd like to introduce to you Caesar.
Hello.
He knows the ins and outs of this machine. This CMM is one of the tools we use when we run quality control on our Fireball products.
I use it to test all the Fireball squares, all the tables, a lot of different things throughout the shop. So whenever we need to test something, this is our go-to baby. Over here we have the stylus. It's gonna be the ruby crystal. Basically really hard material, won't scratch. It's gonna let us get accurate measurements in 3D space. It uses a set of sensors, camera system, tracks me as it moves. As long as I have clear line of sight, it should be giving me a really good measurement. This right here, really reliable. If it tells me something is not flat, something is not square, something is off, I trust it. Today we're gonna be using this table frame to check if these schematics are in fact correct. We're gonna be testing overall dimensions, so length, height, width. So it's gonna be from bottom of the weldment all the way to the top. We're gonna be testing if these legs are twisted in any way, so if it's off or if it even is in the correct place. We're gonna be able to tell that with this machine. So probably throughout the whole part, while I'm testing it, it's probably gonna be like closer to 250, 300 points in total. So you can imagine it's gonna give me a really good picture of how this thing truly is.
Making a perfect frame is virtually impossible, but how far from perfect are these frames allowed to be? Well, the drawings indicate 1/8 of an inch tolerance around the weldment, except for the twist of the frame, which is 1/16. Kind of like the game Operation. If any part of this exceeds the tolerance, it fails. This machine is going to be able to precisely identify each piece down to the thousandths of an inch, completely removing any human error. So the CMM will make sure this weldment is not a parallelogram, a trapezoid, or an irregular quadrilateral. But that's just for measuring the frame. Since we added legs to the drawing, there could be a lot of things keeping them out of alignment. Things like, are they tilted to the left, to the right, or are they leaning inward or outward? How twisted are they? Are they centered front, back, and side to side at the T-joint? And are they even the correct length? All these questions are only taking the dimensions into account. So what about the twist of the frame? Luckily, the CMM will be able to measure the tube distortion by finding the highest highs and the lowest lows. Then we will use the numbers it gives us to see what frames pass or fail.
As long as green light is on, you're good to measure. And then you can just lightly place it on top, push the button, it'll give you a beep, and then you can go crazy. So just light pressure, as long as the light is on, you hear the beep, you got a point. You can go upside down, all the way around. One of the good things that this CMM machine does is you actually take a picture of what you are essentially measuring. It should pop up right there. You can actually see in real time where the stylus is on that picture. So if I start making a plane on this edge right here or this surface, it will show up on that picture with the right perspective to actually seem like it's on that surface. And I'm trying to be very careful. I do not want to move this. If it moves even just a tiny bit, all my measurements are going to be off. So I'm very careful, just letting the ruby hit it. Took about 16 points. Like I said, nothing too crazy. So right here, you can see that plane we just got. In relation to the picture, you know, it looks like what I just measured, and it's at a 6,000th flatness. So if that was one of our tables, it would fail, and Jason would not be proud. This is just a quick demo of the CMM and how it works and what we're gonna be measuring. I got a lot more to go, so I'll let you know when I'm finished. Just let the ruby do the work.
While Caesar's collecting all these data points, let's see if we can visually identify any problems with the frames. Remember how we talked about weld distortion earlier? I have noticed that not a single frame has addressed this issue. They all have a curve to them. And we're not talking any curve. We're talking that exact 1/16 of an inch deviation in all the corners of every single tube. That doesn't even take into account for twist, which we'll check out in a minute. Every one is warped. Flip them over. I know this is accentuating the problem. It's pretty lousy, and they're all this way. Here's two frames that are supposed to be identical. Which way is it? It's so bad. I don't even know which way it goes, or it has to go this way. If I line two legs up the best I can, here's what the other ones look like. I'm gonna line two legs up again. In a perfect world, that's how they should look on this side and this side. This one's pretty good. This is the best out of the three, but we still got some issues here. That's probably within tolerance. While I'm not hopeful from what I've seen so far, Caesar let me know he's done taking measurements.
So I just finished measuring all the frames. Right now what I'm gonna do is I'm gonna go through, get all the measurements I need. So things I'm looking for is overall dimensions, height, length, width. I'm looking for the twist in the bottom frame, seeing if that's flat. We're just gonna go ahead and check the flatness. I have already set to show me flatness whenever I click plane. So you can go ahead and see 106 thousandths. So for this, we should be within a 32nd. So that's 32 thousandths about. And as you can see clearly, we're almost triple that. It is really out of spec on this. So for that reason, this fails. I'm gonna go ahead and wrap the rest up, and I'll go ahead and give the results to Jason.
Let's dive into what Caesar found. Because he collected so much data on each frame, we've broken it down into 4 categories. The first is dimension. 2 out of 6 of the frames passed and were within the assigned tolerances for length, height, and width. Second is perpendicularity. Again, 2 out of 6 of the frames had legs that were close enough to 90 degrees of squareness to the frame and passed. Third is twist. 0 out of 6 frames passed, as all of them were twisted far enough to exceed the tolerances. And finally, it was asked for a matched set to be made. And again, 0 out of 6 were able to have their frames match within the tolerance. So unfortunately, none of them passed. Just to confirm that the CMM is correct, let's look at twist. We know that all the tubes are bowed, making them out of tolerance. But now we have a perfect plane. Let me show you what I'm talking about. We're going back to video 1. Remember, these 2 pieces right here welded together make a perfect plane, 3 points. You weld this one together, perfectly flat, teeter, totter, or warp. But what happens if you don't have a flat table is that this next joint, this joint and this joint is where you get into trouble. Because if your table is crowned or dished or has any weird manipulation, now you have 4 points. 1, 2, 3, 4. And it's gonna follow the surface of your table, which means this is gonna kick up. These 2 points have now introduced twist on this axis. This is why having a flat table is very important. And we're gonna be able to show you that right here. We're gonna identify the corners, but we're twisted right here and right here. This is 1/16 of an inch. This is what the plans call for. You can have this much twist in the part. So I'm gonna push down on this corner, creating those 2 flat surfaces, remember? And then this part's gonna fly right underneath. Not only are these tubes bowed out of spec, the whole frame is twisted too. And we can continue to test that on all of these, and the results are almost exactly the same. It's just wrong in so many ways. Okay, so that's 6 frames that failed. What about the other 6 frames that we did before? That's 12 frames that are not made to size or flatness. I do notice that nobody TIG welded these. Could that have changed the outcome? Maybe. I know they all MIG welded them for speed so you can make money. One of the things we talked about on the forum is the tolerances on the drawing. And unfortunately, as fabricators, we don't get to decide that. That is up to the customer. All we have to do is try to build to their specifications. When you look at a drawing, can you hold tight tolerances? I think being aware of what kind of tolerances you can hit as a fabricator is really important, and that needs to be taken into consideration. So what did we discover? Remember, I added a lot of information in the drawings to improve the quality, and I just did not see that in this instance. I did not see this job taken more or less seriously by adding more complexity to the part. I know one of your concerns was my testing methods on these parts, but by adding the CMM machine, I think I can confidently say that the measuring is correct. Once again, we're left with more questions. Another 6 frames and testing that didn't pass the quality control. So what's causing these frames to fail? Is a speed square and a tape measure, like we saw in the video, good enough for QC? So what tools do you guys think these fabricators need to build and quality control their parts? All of these fabricators told me that their plate steel tables are seriously warped. How much of that is influencing the product that comes out of it? What do you guys think about the weld distortion in these parts? Is that something we as fabricators should be paying more attention to? I have lots more questions for you. We're gonna put all these up at the Fireball Tool forum. I'd love to hear your feedback. We have a lot more investigating to do to get to the root cause of failed parts. Thank you guys for watching, and I'll talk to you at the forum.